you. இல்லைங்க வைஃபை கனெக்ட் ஆகல. இது ஐஐடி வைஃபைக்கு இங்கே பிரச்சனையாக இருக்குது. வைஃபை ப்ராப்ளமாக இருக்காங்க. கீழே வரலாமா? சரி. இல்லை சார் ஒரு அங்கே எனக்கு கிளாஸ் இருக்குது. சரி நான் பார்க்குறேன். சரி. So this is week 12 of the engineering thermodynamics course problem solving session. So what we'll be looking at today is to solve some of the cycles like Brayton cycle, vapor compression cycle, and Rankine cycles, and we'll see some numericals on those. And so till now what we saw is individual process and applied first law and second law for each of the components or a process and evaluated those. So now we'll go a step further and apply a combination of these components which form a cycle, and then evaluate how these cycles are. So we'll apply the same first law and second law, but now for a whole cycle. So to start with, the easiest what we come across in the previous weeks when we studied second law was the Carnot cycle. So that is an ideal cycle and also a reversible cycle. So where we had two reversible adiabatic or an isentropic process and two constant temperature isothermal process. So I'll also go through the Carnot cycle first, so that it's easier to compare an actual reversible cycle with an other cycles which are generally used. So we'll start with the Carnot cycle. So for example, if a Carnot cycle is used to produce power, so and your steam is your working fluid. So if you plot a TS diagram, and this is how it looks for a water or steam as a working fluid. So this is your two-phase envelope in a TS diagram, and then what we have is four process which form the cycle. So we'll start with suppose at D, where you are having a reversible adiabatic compression, and then A to B gets an isothermal compression, or you can say isothermal heat rejection, and then heat addition, and then B to C is your reversible adiabatic or isentropic expansion, and similarly C to D is your isothermal expansion, or you can in a normal cycle we'll have heat rejection when we are replacing this temperature with pressure, so because of pure fluid. So what when you are looking at Carnot cycle, you have two compression and two expansion process. So D to A is and A to B are compression process, and B to C and C to D are expansion process. So A, B and C, D, you have both heat transfer as well as work transfer. So here what we assume is the cycle is operating between your source temperature of 300 degrees Celsius and a sink temperature of 20 degrees Celsius. So ideally we assume there is no temperature difference between your source and the temperature A, B, and similarly C and D and the sink temperature. So this temperature T1 and T2 are fixed to source and sink temperatures. So for this we need to evaluate what is the thermal efficiency and what is the ratio of the turbine work to the compression work if all the processes are reversible. So if this is the case, so we'll evaluate, we know how the thermal efficiency of a Carnot cycle will be. So a simple expression which is 1 minus T1 by T2, which we can get applying first law and second law. So that's all. So what we have, what we get is W by Q. Q is the heat input and W is the work output which you are getting. So net work output we can express as Q1 minus Q2, which is Q in minus Q out divided by Q in. So that you get 1 minus Q1, Q in by Q out. Sorry, 1 by Q out by Q in. So this is directly from the temperature scale which you have seen. You can get the expression for, you can write the Q ratios as temperature ratio. So 1 minus T1 by T2. So substituting the temperature values of the source and sink, what we get the thermal efficiency to be 48.9%. So close to 49% is the efficiency of the Carnot cycle. So with this, but now we need to evaluate what is the work which is developed in the turbine as well as in the compression process, and what is the ratio of this. So for that we'll evaluate each of the process. To do that, what we know is A and B, we know that both are saturated states. So A is your saturated liquid and B is your saturated vapor. So from the steam table, we know for saturated vapor at 300 degrees Celsius, your enthalpy is 2749, and similarly the entropy. So we know Sp, which will be equal to Sc, because B to C is an isentropic expansion process. So from C, we can evaluate what is the quality at C based on the saturated liquid and vapor corresponding to 20 degrees Celsius. So that gives you a quality of 64.6%. So that is your vapor quality. And then at similarly XT is 35.3%. So that is the quality at T. So C and D both are in two phase. So now with the quality known being known at C and D, we can evaluate what is the enthalpies at the state points. So Hc is again Hf plus X into Hfg. So we can find out Hc, which comes out to be 1669.4 kilojoule per kg. And similarly Hd, so Hd here the same expression. So we are just plug in the different quality Hd. So that gives you enthalpy to be 950.8 kilojoule per kg. So now we know all the state enthalpies. So we can apply first law and find out what is the work and heat transfer. So the turbine work per unit mass is the difference between enthalpy at state B and C. So the expansion process during B and C. So the work done in the turbine per unit mass comes out to be the change in enthalpy. So that gives you 1679.6 kilojoule per kg. So this is the work generated in the turbine for the isentropic expansion case. So if you apply steady flow energy equation, that's what you get. And then similarly for compression between E and D, again this the work is equal to the enthalpy difference. So that comes out to be 393.3 kilojoule per kg. Right, 393. So this is just the difference between the expansion and the compression processes. Similarly, we can find out the Q at A, B and CD, so which is T naught delta S. So that will give you the heat transfer, and then we can apply first of all steady-Frobenius equation for the process A to B, and then estimate what is the work done for AB and similarly for CD. So what we can observe here is the total the net work and heat transfer which is happening for each of the process is very large compared to what is the net work which will be generated out of the cycle. So each of the components will be very bulky going within Carnot cycle. Even though the net work, suppose you are getting 1 kilowatt of work, you will be using a very large turbines and heat exchangers for this case to generate the work of 1 kilowatt. So even in the case of building Carnot cycle, it will be a huge task with the capital, in terms of capital. So this is the Carnot cycle which we saw. Now let's move on to Rankine cycle. So in a vapor power cycle, enthalpy of steam at inlet and outlet of turbine are 2800 kilojoule per kg and 1800 kilojoule per kg respectively. If the pump work is neglected, find the specific steam consumption in kg per kilowatt hour. So what is given is you know what is the enthalpy at inlet and outlet of turbine. You need to find out how much is the mass flow rate per unit of work which is to be that is specific steam consumption. How much mass flow rate is required to generate per kilowatt of work. So that's what is been asked. So you know W is m dot into delta H for a turbine. If you apply steady-Frobenius equation, assuming an adiabatic turbine, which is generally the case which we will assume. So, and in that case, Q will be 0, and neglecting kinetic and potential energies, what we get is work is m dot into H out minus H in. Sorry, work equals H in minus H out. So m by W is 1 by H in minus H out. So what we get is 1 by 2800 minus 1800. So we get 1 by 1000. So this is all in kg per second. To convert into hours, we multiply by 3600. So 3600 divided by 1000, that gives you 3.6. So that is your specific steam consumption for this cycle. So we look at Brayton cycle. So Brayton cycle is, you see, is similar to an Carnot cycle. So you have, instead of constant temperature, you have constant pressure processes happening. So and this is a gas driven cycle. So you have that is your Brayton cycle. You have isentropic compression, and then isobaric heat addition, and then isentropic expansion, and then similarly isobaric heat rejection. So that is your Brayton cycle. So here in this problem, what is given is consider a simple Brayton cycle using air as the working fluid, which has a pressure ratio of 12 and has a maximum cycle temperature of 600 degrees Celsius, and operates the compressor inlet at 100 kilopascal and 15 degrees Celsius. So the pressure ratio is given, so you know straight away what is the P2 by P1, and the maximum cycle temperature is 600 degrees Celsius, and it operates the compressor inlet at 100 kilopascal and 15 degrees Celsius, which will have the greatest impact on the back work ratio. So what is the work ratio, inlet to outlet work given in by the work used? A compressor isentropic efficiency of 80% or a turbine isentropic efficiency of 80%. So we can assume a constant specific heat at room temperature. So we need to find out which efficiency of the compressor or turbine affects the total efficiency or the back work ratio more. So if you assume this is your TS diagram for a Britten cycle. So ideally we have 1 to 2s, and then 3 is heat addition and 3 to 4s isentropic expansion, but we go for 3 to 4 because the compressor and the turbines are not 100% efficient. So we have some isentropic efficiency of 70%, or in this case 80% given. So from then you have rejection, heat rejection. So to estimate first for a compressor, we'll assume just the compressor here. So what we know is the pressure ratio. So for an isentropic process or an reversible adiabatic process, we know PV raised to power gamma is constant. So in terms of temperature, what we get is T2 by T1 equals P2 by P1 raised to power gamma minus 1 by gamma. So T1 is known inlet to the compressor. So that is 288 Kelvin, which is 15 degrees Celsius, multiplied by 12, which is the pressure ratio raised to power gamma for air is 1.4. So 0.4 by 1.4 gives you the outlet temperature for an reversible adiabatic compression to be 585.8 Kelvin. And similarly, the compressor efficiency is given to be 0.8. So for the compressor efficiency is defined, isentropic efficiency is defined as the isentropic compression work divided by the actual work. So the isentropic compression work is H2S minus H1 divided by H2 minus H1. H2 minus H1 is the actual compression process, and 1 to 2S is your isentropic compression process. So H2S minus H1 divided by H2 minus H1, isentropic work divided by your actual work. So if we assume enthalpy, the specific heat doesn't vary, we have a perfect fluid. So in that case, so we can write H2 minus H1 as Cp T2 minus T1. So what we get is the isentropic efficiency written in terms of temperature. So rearranging that, we get T2 equals T1 plus T2S minus T1 divided by your isentropic efficiency of compressor. So we have already found out what is the temperature at T2S, which is 585.8, and substituting the inlet value temperature, we get T2 to be 660.2 Kelvin. So that is the temperature at the outlet of compression process. Similarly, the expansion. So here what they have given is the maximum cycle temperature to be 600 degrees Celsius. So if you see here in a TS diagram, the maximum temperature occurs at 3, which is the temperature at the inlet to the expander or the turbine. So T3 is 600 degrees Celsius. So we know the inlet to the turbine. So similarly, the same process which we applied the compression, we will apply to the expander as well. So we get T4S equals T3 into P4 by P3 raised to power gamma minus 1 by gamma. So P4 by P3 is 1 by your pressure ratio 1 by 2L, and T3 is 600 plus 273, which is 873 Kelvin. So substituting, we get T4S as to be 429.2 Kelvin. And the turbine efficiency is given by, in this case for turbine it will be actual work divided by the isentropic work. So the turbine efficiency will be H3 minus H4 divided by H3 minus H4s. So writing in terms of Cp delta T's and rearranging the temperature values, what we get is T4 equals T3 minus turbine efficiency into T3 minus T4s. So substituting the values here, T3 we know, which is 600 degrees Celsius or 873 Kelvin, and T4s which we have found out, which is 429.2 Kelvin, and your turbine efficiency is given as 0.8. So that gives you the turbine efficiency to be 518 Kelvin. The temperature at the exit of the turbine to be 518 Kelvin. So now we find out what is the work done for an ideal compression process, which is an isentropic compression process, and similarly for the actual compression with the isentropic efficiency of 0.8, and similarly for turbine. So if we do that, what we get is, so if we assume what is per kg of your air, what is the compression work or the specific work, what we get is for isentropic compression we get Cp T2s minus T1, which comes out to be 299.3 kilojoule per kg, and similarly the actual compression work is Cp T2 minus T1. So substituting the values, that comes out to be 374.1 kilojoule per kg. And the turbine, in case of turbine, the isentropic expansion for turbine gives you a work of 446 kilojoule per kg, and with the 0.8% efficiency you get the actual turbine work to be 356.8 kilojoule per kg. So if we have a back work ratio of 80% efficient compressor and isentropic turbine case, which is been asked, which is better. So in that case, your back work ratio is your compression work divided by the turbine work, whatever work which you are generating, the part of which is being used for compression. So that's what this means. So your actual compression work is 374.1 divided by the turbine isentropic turbine, which is 446. That gives you the back work ratio to be 0.8387. Similarly, back work ratio of turbine, if it is 90% efficient, 80% efficient, so in that case the back work ratio, again if you substitute the values, comes out to be 0.8387. So the two results are identical. So the other way of doing it, instead of going all the way through, is you can first define the compressor back work ratio, which is compressor work divided by the turbine work, and we know if the efficiency of the compressor is your isentropic work divided by the actual work. So the actual work will be isentropic work divided by 0.8. So you substitute both the expression, which will give you 1 by the efficiency of the compressor or the turbine multiplied by your isentropic compression work divided by isentropic turbine work. So both will give you your back work ratio divided by 0.8, or you can say the actual back work ratio is back work ratio of an ideal compressor and expander divided by the efficiency of compressor multiplied by efficiency of turbine. So in this case, being the efficiency being both same, we'll get both the back work ratio to be same. So the two results will be identical. I think I'll add that as well. So here if I write okay, Next is a Rankine cycle. So in this case, Rankine cycle, the process remains same. So instead of operating in a vapor side or gas side, what we do is we operate in a two-phase system. So we have a cycle which is brought inside the vapor dome. So since the operating fluid is if there is a pure fluid, your constant temperature process is also a constant pressure process. And Brayton cycle is a constant pressure process. So in this case, what you get is part of the process will be a constant temperature process, which is equivalent to a Carnot cycle. So that is your Rankine cycle. So you have vapor dome here. So 1 to 2 is your compression process. So here you pump, because this is a cool liquid, you pump the liquid from 1 to 2, and then from 2 to 3 you heat the liquid. So the subcooled liquid is then converted to steam and then expanded in the turbine, which is 3 to 4, and then the heat is rejected in heat exchanger from 4 to 1. So this is your process in a Rankine cycle. So what we assume the question is given is the compression and the expansion are adiabatic. So there is no heat transfer. Then the change of kinetic and potential energies are negligible, and the dissipation is neglected, and we have a steady state operation. So what is given data which is known for the cycle is the maximum pressure is 40 bar, and then the temperature at point 1, which is the inlet to the pump, is 35 degrees Celsius, and the temperature at the outlet is 35.14 degrees Celsius, which will be generally the case when you are pumping the fluid to higher pressure. Since it's subcooled liquid, the change in temperature will be very minimal. So ideally you can assume the pressure subcooled liquid to be correspondingly to that temperature, the saturated liquid enthalpies. So the next is what is given is an average specific volume of liquid water, which is 0.0010043 meter cube per kg, and then water mass flow rate is given as 7 kilograms per second, and a table is also given for giving the data of the saturated states of the water. You have both saturated liquid and as well as saturated vapor data is provided here. And then what we need to find out is the thermodynamic state points at 2 and 4, and what is the work and heat transfer during each of the process, and the efficiency of the cycle. So we know pressure, we know at T1 your saturated liquid temperature is 35 degrees Celsius. So the corresponding pressure is your saturated pressure is your operating pressure at 1 and 4, and the maximum pressure is your pressure at 2 and 3, so that is 40 bar. So the data here is given for the saturated liquid and vapor. So what we know is we know at 1, 2 and 3. So the only unknown is at 4. So which will be a two-phase which we can calculate. So S2 is equals to S1, and since the pump work in case is dH is minus VdP integral. So if you write the TdS relation, dH is TdS minus VdP, since your entropy change is 0 or it's a constant isotropic process. So what we get is dH equals minus VdP. So integrating that, what we get is V into delta P is your change in enthalpy for the compression process. So V is given, you know, the pressure, operating pressures, so 40 bar, and the pressure corresponding to 35 degrees Celsius, which is 0.056 bar. So substituting that and converting into pascals, what we get is pump work to be 4.017 kilojoule per kg. So using this, we can now estimate the enthalpy at the pump exit. So the pump exit will be H2 is H1 plus delta H. So H2 comes out to be 150.577 kilojoule per kg. The inlet is 146.56, the outlet is 150.577 kilojoule per kg. And similarly, for process 3 to 4, the expansion is also a reversible adiabatic, so we can assume the entropy to be same. Entropy at S4 equals S3, which is equal to 6.0685. So now what we know is the entropy at here. So we can, using the saturated liquid and saturated vapor entropies, we can estimate the quality at state 4. So the quality at state 4 comes out to be S4 minus your saturated liquid entropy divided by saturated vapor entropy minus saturated liquid entropy. That gives you quality to be 0.709 or 70, close to 71%. So the enthalpy at 4 is, using the quality, this saturated liquid enthalpy plus quality into your latent heat at that corresponding to that pressure. So that gives you H4 to be 1861.02 kilojoule per kg. So we know now all the enthalpies of all the state points. So now we can estimate the work. So for process 1 to 2, which is the compression process or the pumping process, we have the pump work, which is mass into H2 minus H1. Mass is given as 7 kg per second. So 7 into H2 minus 1 H1 gives you 28.1 kilowatts. And since it's an adiabatic process, your Q is 0. Similarly, for process 2 to 3 is heat addition process. In this case, your work done is 0, and heat addition is mass times H3 minus H2. So that comes to be 18,548.1 kilowatts. So that is the heat which is being added to the cycle. And similarly, process 3 to 4, which is the expansion process in the turbine, that comes out to be mass times H3 minus H4. We found out both the enthalpies. We substituting, we get work done in the turbine to be 6575 kilowatt. So we see the comparison of the work, the pump work is negligible. And then process 4 to 1 is heat rejection. So in case of heat rejection, your work done is 0, and Q out is 12,001.2 kilowatts. The efficiency of the cycle, the Rankine cycle, is your net work divided by the net Q which is supplied. So the net work is the turbine work minus the pump work divided by the heat which has been supplied. So the efficiency of the Rankine cycle comes out to be 35.3%. So that is the efficiency of this Rankine cycle. Question. So next question again on Rankine cycle. So what we have is consider a steam power plant operating on the ideal Rankine cycle. So steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. So determine the thermal efficiency of this power plant. The thermal efficiency if steam is superheated to 600 degrees Celsius instead of 350 degrees Celsius, that is your part B. And the part C of the question is the thermal efficiency if the boiler pressure is raised to 15 megapascal while the turbine inlet temperature is maintained at 600 degrees Celsius. So those are three parts of the question. So what is asked is, so first initially an ideal Rankine cycle is operating between 3 megapascal and 10 kilopascal. So what essentially is been asked is indirectly is to find out how the cycle changes or the efficiency of the cycle varies when you are superheating it to a higher temperature. So what will happen if you are superheating the steam which is entering the turbine to a higher temperature? That's the part B of the question. And the part C is instead of operating at 3 megapascal, now you are operating at a higher pressure which is at 15 megapascal. So in this case, how is your efficiency varying? So those are the two parts to the question, the modifications are made and is it beneficial or not. So that's what we've been asked to analyze. So to start with, the first is to a simple Rankine cycle which we are seeing. So which is operating between 3 megapascal and 10 kilopascal, and your temperature at the inlet to the turbine is 350 degrees. That's the data which is being given. So if you draw a TS diagram, so this is what you get. You have a vapor dome. So we have operating between 10 kilopascal and 3 megapascal. So and all the four processes. So what we know is one is your saturated liquid. So from here to 2 we are pumping it. So we can straight away get the enthalpy at 1 and using the same process which we did previously. So since the specific volume at 1 is known and the pressure differences are known, so we can estimate the enthalpy at 2, and the enthalpy at 3 is also known because to locate this point we know we need two state points and that is known, pressure and temperature is known. So pressure is 3 megapascal and temperature is 350 degrees Celsius. So we can find out the enthalpy and entropy at state 3, and once we know the entropy at state 3, so entropy at state 4 is straightforward. So S3 and S4 are same, and using entropy at state 4 we can then determine the quality, and using the quality then determine the enthalpy. So that's the process to determine all the state points. So that's what been listed here. So state 1 initially we know the saturated liquid at 10 kilopascal, so that enthalpy is 191.81 kilojoule per kg, and similarly the specific volume at state 1 which is 0.00101 meter cube per kg, and then the pressure at 2 is 3 megapascal. So since S2 and S1 are same, so the pump work can be written as P into delta P. So substituting the values, what we get is pump work to be 3.02 kilojoule per kg. So H2 minus H1 is your delta H, which you get the pump work, so specific pump work. So what you get is H2 is H1 plus the specific pump work, which is 194.83 kilojoule per kg. And similarly from the superheated steam table, P3 and is 3 megapascal and P3 is 350 degrees Celsius. So your enthalpy is 3116.1 kilojoule per kg, and entropy is 6.745 kilojoule per kg Kelvin. And same we can estimate the saturated liquid and saturated vapor entropy values for 10 kilopascal, and since S3 is equal to S4, the quality at 4 comes out to be 81.28%. So using that we can estimate the enthalpy at 4, so which is equals to 2136.1 kilojoule per kg. So the heat added for the process is Q in is H3 minus H2, which is 2921.3 kilojoule per kg. And similarly, the heat rejected for this process is H1 minus H4, or H4 minus H1 in the absolute quantity terms, which comes out to be 1944.3 kilojoule per kg. So the thermal efficiency for the cycle is W net by Qn, or we can write 1 minus Q out by Qn, because for a cycle the net work is equals to your net Q net. So the thermal efficiency for this simple cycle turns out to be 33.4%. So the second case, the part B of the question is when you have increasing the inlet temperature to the turbine from 300 degrees Celsius, 350 degrees Celsius to 600 degrees Celsius. So in that case, your enthalpies at 1 and 2 will remain same. So only state points which are getting affected is your state 3 and 4. So H3 is now, instead of 3 megapascal and 350, 3 megapascal and 600 degrees Celsius. So the enthalpy corresponding to it is 3682.8 kilojoule per kg. And similarly, estimating the quality, so the quality comes out to be 0.915. So previously the quality was 0.8128. So now increasing the superheat temperature, so that pushes the quality also towards the saturated vapor. So we are getting higher vapor quality at the exit, which is good. So that's what is needed. So from 81% it is now jumped to 91.5%. So the corresponding enthalpy at this point is 2380.3 kilojoule per kg. So the Q in is H3 minus the heat added is H3 minus H2. So it comes out to be 3682.8 minus 194.83. So Q the net heat added is 3488 kilojoule per kg, and similarly the heat rejected is H4 minus H1, which is 2188.5 kilojoule per kg. So in this case the thermal efficiency is 37.3%. So if you see the thermal efficiency increasing the superheat temperature from 350 to 600 has increased your efficiency from 33.4% to 37.3%, which is 3.9% increase. So, and the added advantage in this case is your quality of the steam is also increasing from 81.3% to 91.5%. So which is good because we will not encounter two phase in the turbine, so which will create its own set of problems. So we always want the turbine to operate at a single phase or a vapor state. So having two phase will erode and deteriorate the performance of the turbine. So having this increase in quality is a good sign. And then if we are increasing the condenser pressure to 15 megapascal, so again in this case what we are doing is, in this case H1 will remain same, but the other enthalpies will vary. So we need to evaluate using the same process which we did in the part A of the question. So we'll follow the same to estimate each of the enthalpy values. So from state 2, instead of 3 megapascal, now it has jumped to 15 megapascal. So the enthalpy at exit of the pump will now be 206.95 kilojoule per kg, and similarly H3 is 15 megapascal and 600 degrees Celsius. So in this case the enthalpy is 3583.1 kilojoule per kg, and H4 is 2115.3 kilojoule per kg. So in this case what has happened is in the quality, so previously jumped from 81.3% to 91.5%, but increasing the condenser pressure now has reduced the quality to 80.4%. So there is a moisture at the exit. So now for this case, if you evaluate the efficiency, so for that, what is the heat input is 3376.2 kilojoule per kg, and heat out is H4 minus H1, which is 1923.5 kilojoule per kg. So the thermal efficiency is 1 minus Q out by Qin, which comes out to be 43%. So what we can observe here is increasing the condenser pressure increases your efficiency, but the drawback here is your steam quality decreases. So that is one thing to be careful of. So one of the option to increase the thermal efficiency, the cycle is to operate at a higher pressure, but now the quality also reduces. So but if you want to increase the quality, then we have to go back, increase the superheat. So but doing so, we need your temperature to be at very high, and that requires your source temperature to be at very high temperatures. So which is difficult, or in this case so that's one of the option. So that is regarding the Rankine cycle. So now we go and consider the following statements regarding the Rankine cycle for steam power plants. So first is Rankine efficiency of steam power plant is higher in the winter season compared to the summer season. So this high Rankine efficiency in winter season is because of the low condenser temperature. So what are the options? Which are both the statements correct or incorrect? So what they say is Rankine efficiency of steam power plant is higher in the winter season compared to the summer season. So this high Rankine efficiency in winter season is because of the lower condenser temperature. So the answer is both are incorrect. So which one of the following statement is correct? Work ratio and efficiency of Carnot cycle is higher than the Rankine cycle. Work ratio and efficiency of Carnot cycle is lower than the Rankine cycle. Both the Carnot and Rankine cycle have equal work ratio and efficiency. So work ratio of Carnot cycle is low and the efficiency is high in comparison to the Rankine cycle. The answer is option D. So work ratio in terms of Carnot cycle will always be low, but the efficiency wise the Carnot cycle will have a higher efficiency, so which we have already seen. So if you see Rankine cycle, the pump work is very small, so it's negligible. So if you take the work ratio, so turbine by work the pump work, which will be very high for Rankine, but in Carnot cycle both are comparable, so that will give you a lower Carnot work ratio. next is we see in another Rankine cycle problem. So a steam power plant working on ideal Rankine cycle has the boiler outlet pressure of 1000 kilopascal and the condenser pressure of 100 kilopascal. Find 1 turbine output, 2 pump work, and 3 heat input, 4 cycle efficiency, 5 steam rate, and 6 moisture at the end of the turbine. So what is given is the pressures, the operating pressures 1 megapascal and 0.1 megapascal, and similarly the enthalpies and entropies at the state points. So H1 is your saturated vapor saturated vapor condition. So it comes so your enthalpy is 2778.1 kilojoule per kg, and similarly S1 is equal to your saturated vapor entropy again. So that comes out to be 6.5864, and what we know is S1 is equal to S2S, but here it's an ideal reversible cycle, and similarly H3 is your saturated liquid condition. There your enthalpy is 417.16 kilojoule per kg and the entropy is 1.3025, and the latent heat is given at 0.1 megapascal or 100 kilopascal, is 2258 kilojoule per kg, and similarly the change in entropy for saturated vapor to liquid is 6.0588 kilojoule per kg Kelvin. So what we know is S2S is S3 into X2S into SFG. So substituting the value X2 or the quality at 2 comes out to be 87.21%, and using this we can estimate the enthalpy. So enthalpy comes out to be 41 enthalpy of liquid plus quality into your latent heat. So H2S comes out to be 2386.36 kilojoule per kg. So work input to the pump is H4S minus H3. So at state 3 the working fluid is a saturated liquid. From the steam table the specific volume is H4S minus H3. So at state 3 the specific volume is 0.001 meter cube per kg. So my pump work is integral VdP. So it is specific volume into a change in pressure. So that comes out to be 0.001 multiplied by 1000 minus 100. So that comes out to be 0.9 kilojoule per kg. Next is we need to find out the turbine work. Turbine work is H1 minus H2S. So H1 is 2778.1 minus 2386.36 gives you the work output of the turbine is 391.74 kilojoule per kg. So the net work is the turbine work minus pump work. So the net work comes out to be 390.84 kilojoule per kg. So next is we need to find out the enthalpy, the heat input. So for that we need to know the enthalpy at 4S. H4S is from the pump work comes out to be 418.1 kilojoule per kg. So heat input is now H1 minus H4S. So 2778.1 minus 418.1 gives you 2360 kilojoule per kg. that is the heat input. So the cycle efficiency now can be found out. So net work divided by heat input. So net work is 390.84 divided by 2360. So that gives you the efficiency of cycle to be 16.56%. The steam rate is 3600 divided by the net work. So 3600 divided by 390.84 gives you 9.21 kilograms per kilowatt hour. So that is the steam rate. So the moisture content in the steam at exit is 1 minus X2S. So that is 12.79%. So next is the next question is the other example, if the pump work is considered negligible, calculate the cycle efficiency and steam flow rate. If the turbine has an efficiency of 75%, calculate the efficiency, moisture content and steam flow rate. So assume pump efficiency as 0.75 or 75%. So from the previous example which we did, the turbine work is 391.74 and the pump work can be neglected to be 0. So the net work will be the turbine work, which is 391.74 kilojoule per kg. And Q1 is H1 minus H3. So for the first case, if the pump work is 0, so the heat input is 2778.1 minus 417.46, which gives you Qin is 2360.94 kilojoule per kg. So the efficiency of the cycle in this case is net work divided by the heat input, which is 16.6%. So if you see the previous case, it was 16.56%, so which is negligible. So which is also true because the pump work is very small, 0.9, so that's what is being getting added, so it is 16.6%. So the steam flow rate will also not vary much. So in the previous case is 9.21, in this case it has reduced to 9.19 kilojoule per kilowatt hour. So the second part of the question is what is important. So here when we assume the turbine efficiency is 75% and the pump efficiency is 75%. So in this case the turbine efficiency is your actual work divided by the isentropic work. So what we found out previously is the isentropic work. So the actual work will be the efficiency times the isentropic work, which is 0.75 times the work done in the previous problem. So 0.75 into 391.74. So that gives you the turbine work to be 293.8 kilojoule per kg. So the input work is WP by efficiency of the pump. So 0.9 by 0.75 gives you 1.2 kilojoule per kg. The net work is your WT minus WP, so which is 293.8 minus 1.2, which gives you 292.6 kilojoule per kg. So that is the net work. And H4 is H3 plus WP. So H4 is 418.36 kilojoule per kg, and the heat input is increased to 2359.74. So previously it was 2360.94. It has now become 2359.74 kilojoule per kg. So the efficiency of the cycle is now W net by Qn. So that comes out to be 0.124, 12.4%. Previously it was 16.6%. So having a 75% efficiency of the turbine has reduced it to 12.4%. So to find out the quality, so we know H2. So from there we can find out what is the quality. Substituting we get quality to be 91.55%. So moisture content will be 1 minus of this. So moisture content exit of the turbine is 8.45%. So steam rate will be again 3600 divided by W net. So that comes out to be 12.3 kilojoule per kilowatt hour. So that has increased. So this is more steam flow rate required. So previously it was 9.19, but now it has increased to 12.3. So having 75% efficiency turbine and pump has increased your steam flow rate requirement, and also your work done has reduced and efficiency has reduced. And but it has improved your moisture content. So it previously it was 12.79%, but now it is 8.45%. So a similar question on Brayton cycle. A gas turbine power plant operating on ideal Brayton cycle has a pressure ratio of 8. The gas temperature is 300 Kelvin at the compressor inlet and 1300 Kelvin at the temperature in turbine inlet. Utilizing the air standard assumptions, determine the gas temperature at the exit of the compressor and the turbine, B the back work ratio, and C the thermal efficiency. So what we know is the turbine, the gas temperature to the compressor and the turbine, and the pressure ratio is given. So we need to find out the exit temperature, the back work ratio, and thermal efficiency. So to find out, first we need to estimate the enthalpies. So we'll use the same approach. So this being an ideal compression process, so 1 to 2 and 3 to 4, T2S is T1 into P2 by P1 raised to by gamma minus 1 by gamma. So with that we can estimate the temperature at the exit for both compressor and the expander. And from the table, so now once we know the temperature and the pressure is known, can estimate the enthalpies corresponding to the pressure P1 as 1 and P2 as 8, so corresponding temperatures. So we can estimate the enthalpy, and the enthalpy comes out to be H2 is 544.35, H1 is 300.19, and similarly for the turbine is H3 is 1395.97, and H4 is 789.37. So with this, the total work in the for the compression process is 244.16 kilojoule per kg, and for the turbine is 606.6 kilojoule per kg. Back work ratio for this is the compressor work divided by the turbine work. So the compressor work is 244.16 divided by turbine work 606.6, gives you back work ratio of 40.3%. So next is the thermal efficiency. So thermal efficiency of the cycle is, for that we need to find out the Qin. So Qin is H3 minus H2, H3 minus H2. So that is 1395.97 minus 544.35 gives you a heat input of 851.62 kilojoule per kg, and the net work is your W out minus W in, which is 606.6 minus 244.16 gives you a net work of 362.4 kilojoule per kg. So the thermal efficiency is W net by Qn, which is 362.4 divided by 851.62, gives you an efficiency of 42.6%. So another way of writing thermal efficiency is 1 minus Q out by Qn. So Q out is H4 minus H1 is 789.37 minus 300.19. So that gives you Q out is 489.2 kilojoule per kg. So substituting that also will give you the same thermal efficiency of 42.6%. So next is the same Brayton cycle, but with the turbine and compressor efficiencies of 80% and 85%. So in this case, how the cycle will change, or how the efficiencies and state points will vary. So that's what we'll be looking at. So what is given is a compressor efficiency of 80% and turbine efficiency of 85%, and rest of it all will given remain same. So we know T1 is 300 Kelvin and T3 is 1300 Kelvin, and the pressure ratio is 1 and 8 bar. So for this we need to find out the given whatever asked. So the compressor work, which we have already found out in the previous problem, so which was the ideal case 1 to 2s. So 2s can be directly found out using the isentropic process, reversible adiabatic. So PV raised to power gamma is constant. So what we get is, if you write in terms of pressure and temperature, we get T2 by T1 equals P2 by P1 raised to power gamma minus 1 by gamma. So from there we know we can find out T2, we know the pressure ratio, we know the inlet temperature, so we can find out T2. So 2 and 1 is known, pressure and temperature is known. From the air standard table you can estimate, find out the enthalpies. Or you can use, if it's an ideal gas assumption, if and Cp is not varying, you can use Cp delta T. And similarly for 3 to 4 S, the same process, reversible adiabatic expansion process. So same way we can find out 4S, and then we can find out the enthalpies or the work done. So here the compressor work is the W1 W2S minus W1 divided by the compressor efficiency. This is the isentropic work divided by the compressor efficiency. So the compressor work is then 305.2 kilojoule per kg, and similarly the turbine work is your turbine efficiency multiplied by the isentropic expansion work. So the turbine efficiency is 0.85, so multiplied by the isentropic work, which will be coming out to be 606.6. so that gives you the actual work done in this case is 515.61 kilojoule per kg. So now we have found out the individual work. So next with this we can find out the back work ratio, or what is the fraction of work which is being used for compression. So W compression divided by the W turbine, so that gives you 305.2 divided by 515, which is 0.592 or 59.2%. So this is the compressor, says that it compressor consumes 59.2% of whatever work is being produced in the turbine. So this has increased from 40.3% to 59.2%. So previously when it was an isentropic case, so this back work ratio was 40.3%, but now with the efficiencies given, it has increased to 59.2%. So this is because of the irreversibility that is occurring in the compressor and turbine. Next is if the air leaves the compressor at higher temperature and enthalpy. So the compressor in is actual H2A is H1 plus W compressor in. So H1 will be, H2A will be 605.39 kilojoule per kg. So based on this enthalpy and pressure value, the T2A comes out to be 598 Kelvin. And similarly, now once we know H2A and H3, we can find out what is the heat added. So Qn is H3 minus H2A. So that is 1395.97 minus 605.39, which comes out to be 790.58 kilojoule per kg. And the net work which is generated is W out minus W in, which is 515.61 minus 305.2, which equals 210.41 kilojoule per kg. So the total thermal efficiency is the net work divided by the heat added, which comes out to be 210.41 divided by 790.58, which comes out to be 26.6%. So this efficiency, if you see, has dropped from 42.6% to 26.6%. So 42 to 26. That's a huge drop in efficiency. So previously with an ideal compressor and the turbine, your efficiency was 42.6. So with your compressor efficiency of 80% and turbine of 85%, your back work ratio has increased from 40.3% to 59.2%, and another your efficiency has dropped from 42.6% to 26.6%. So this is the actual cycle efficiency, and then this is because of the irreversibility on that which is defined by the isentropic efficiency of the turbine and your compressor. And then what we need to find out is the actual temperature out of the turbine. So actual turbine out is your W of the turbine is H3 minus H4A. So H4A is H3 minus W turbine. So H4 actual enthalpy at exit of the turbine is 880.36 kilojoule per kg. So T4A is 853 Kelvin. So with that, I think I finished the problems on Brayton and Rankine cycles. So we have some more problems on vapor compressed cycle, which we'll be seeing on Thursday, which we'll have a review class. So we'll see some problems on vapor compressed cycle and also go through the course, cover the topics which are the major topics which are covered in the course. We'll just have a recap on those. So with that, finish the questions for today. So we'll have a review class on Thursday, and thanks for joining, and see you on Thursday at 5.